Supreme mathematics proposes a unique perspective, one that challenges the way we typically think about numbers. In this system, numbers are not merely symbols of quantity or tools for calculation. Instead, they are seen as living representations of fundamental qualities and concepts that shape our existence. Each number carries its own unique energy, its own story, and its own lesson, offering a new way to interpret the world around us. This approach invites us to look beyond the surface, to see numbers as more than just abstract figures, but as keys to understanding the deeper patterns of life. Imagine a universe where numbers are not just tools for calculation, but keys to unlocking hidden truths about the nature of reality, our purpose and our place in the grand scheme of things. In this vision, mathematics becomes a bridge between the physical and the metaphysical, connecting the tangible world we see with the invisible forces that guide our lives. Numbers become a language, a cosmic code that can reveal the mysteries of existence if only we learn how to read it. This perspective encourages us to ask deeper questions. What does each number mean? How do these meanings relate to our lives, our choices, and our destinies? This system, developed by Allah the Father in the 1960s, assigns deeper meanings to numbers 0 through 9. Born out of a desire to empower individuals and communities, supreme mathematics was created as a tool for self-discovery and enlightenment. Allah the Father, a visionary leader, saw the potential for numbers to serve as guiding principles, helping people navigate the complexities of life. By giving each digit a specific meaning, he offered a new way to interpret both personal experiences and the broader world. Each digit becomes a symbol representing a principle or aspect of the universe and human experience. For example, the number 1 might stand for knowledge, while 2 could represent wisdom, and so on. These meanings are not arbitrary. They are carefully chosen to reflect the building blocks of reality and the journey of personal growth. Through this lens, numbers become more than mathematical constructs. They become guides, teachers, and companions on the path to understanding ourselves and the universe. What come after 100 in numbers? You have 100,000, million, billion, trillion, quadrillion, quintillion, sextillion, octillion, and nonillion. It's like a cosmic code waiting to be deciphered. Each number holds a secret, a lesson, or a message that can help us unlock new levels of awareness. By studying this code, we can begin to see patterns and connections that were previously hidden, gaining insights into the nature of reality itself. By understanding the meanings behind these numbers, adherents believe they can gain a deeper understanding of themselves, their communities, and the world around them. This knowledge is not just theoretical. It's meant to be lived, applied, and shared. It encourages self-reflection, personal growth, and a sense of unity with others who are also seeking truth. In community settings, these ideas foster dialogue, connection, and a shared sense of purpose, as people come together to explore the mysteries of the universe through the lens of supreme mathematics. It's a way of seeing the interconnectedness of all things, a cosmic web woven together by the language of mathematics. Through this perspective, every person, every event, and every experience is part of a larger pattern, a grand design that can be understood through the study of numbers. Supreme mathematics invites us to become explorers of this cosmic code, to seek meaning in the patterns that surround us, and to recognize our place within the infinite tapestry of existence. These numerical meanings offer a framework for understanding our place in the universe. For instance, the number 1 knowledge represents the potential of the human mind, while 2, wisdom, emphasizes the importance of applying that knowledge responsibly. 5%ers see themselves as symbolic, the all, embodying the divine potential represented by the number 7. They believe in using knowledge and wisdom to uplift themselves and their communities, striving for justice and equality. This system encourages introspection and self-reflection. By understanding the meanings behind the numbers, individuals can gain a deeper understanding of their own strengths, weaknesses, and potential. It's about aligning oneself with the cosmic principles represented by the numbers. In mathematics, more specifically algebra, abstract algebra or modern algebra is the study of algebraic structures, which are sets with specific operations acting on their elements. Algebraic structures include groups, rings, fields, modules, vector spaces, lattices, and algebras over a field. The term abstract algebra was coined in the early 20th century to distinguish it from older parts of algebra, and more specifically from elementary algebra, the use of variables to represent numbers in computation and reasoning. The abstract perspective on algebra has become so fundamental to advanced mathematics that it is simply called algebra, while the term abstract algebra is seldom used except in pedagogy. Algebraic structures with their associated homomorphisms form mathematical categories. Category theory gives a unified framework to study properties and constructions that are similar for various structures. Universal algebra is a related subject that studies types of algebraic structures as single objects. For example, the structure of groups is a single object in universal algebra, which is called the variety of groups. In abstract algebra, group theory studies the algebraic structures known as groups. The concept of a group is central to abstract algebra. Other well-known algebraic structures, such as rings, fields, and vector spaces, can all be seen as groups endowed with additional operations and axioms. Groups recur throughout mathematics, and the methods of group theory have influenced many parts of algebra. Linear algebraic groups and Lie groups are two branches of group theory that have experienced advances and have become subject areas in their own right. Various physical systems, such as crystals and the hydrogen atom, and 3 of the 4 known fundamental forces in the universe, may be modeled by symmetry groups. Thus, group theory and the closely related representation theory have many important applications in physics, chemistry, and materials science. Group theory is also central to public key cryptography. Group theory is a branch of abstract algebra that studies groups, which are sets with a binary operation satisfying certain axioms. It's essentially the study of symmetry-preserving transformations and has applications in diverse fields like physics, chemistry, and cryptography. A group is a set with a binary operation that combines any 2 elements to produce a third element within the set, and this operation must satisfy certain properties: associativity, identity element, and inverse element. Group theory is fundamentally about the study of symmetry. It provides a framework for mathematically encoding and understanding symmetries in various objects and systems. Group theory has a wide range of applications, including physics, modeling symmetries in physical systems like crystals and atoms, and understanding fundamental forces in the universe; chemistry, predicting molecular structures and properties and analyzing molecular vibrations; cryptography, developing secure cryptographic algorithms; mathematics, exploring various mathematical structures and relationships. Real analysis and complex analysis are both branches of mathematical analysis, but they differ in the types of numbers they deal with and the functions they study. Real analysis focuses on the properties of real numbers and real-valued functions, while complex analysis deals with complex numbers and complex-valued functions. Real numbers and real-valued functions, sequences and limits, continuity, differentiation, integration, and sequences of functions. Studying the properties of continuous and differentiable functions, evaluating definite integrals, and exploring the behavior of infinite series. Real analysis can be more pathological, with examples of functions that are continuous everywhere, but nowhere differentiable, or sets with zero measure. Complex numbers and complex valued functions, holomorphic analytic functions, Cauchy's integral formula, power series, and contour integrals. Studying the properties of analytic functions, evaluating complex integrals using residue calculus, and exploring conformal mappings. Complex analysis often exhibits a nicer behavior, with differentiable functions being automatically infinitely differentiable and analytic functions having unique properties. Key differences and relationships are real analysis deals with the real numbers, while complex analysis deals with complex numbers, which are extensions of real numbers with an imaginary part. Real analysis studies functions of a real variable, while complex analysis studies functions of a complex variable. Both fields have important applications in various areas of mathematics, physics, and engineering, with complex analysis being particularly useful in solving certain types of differential equations and evaluating integrals, while distinct, real and complex analysis are related. For instance, the theory of complex analysis can be used to evaluate real integrals. Real analytic functions can be viewed as restrictions of complex analytic functions. Advanced calculus, also known as real analysis, is a rigorous mathematical course that delves deeper into the foundations of calculus, focusing on the properties of real numbers and functions and the formal proofs underlying calculus concepts. It builds upon the foundational knowledge of single and multivariable calculus, introducing students to the rigorous language of mathematical analysis, including the epsilon-delta definition of limits, continuity, and differentiability. Here's a more detailed breakdown. Advanced calculus aims to provide a mathematically sound understanding of the core concepts of calculus, moving beyond the computational aspects and delving into the underlying principles. A significant emphasis is placed on constructing formal proofs, solidifying the understanding of mathematical theorems and concepts. The course explores the structure and properties of the real number system, including the completeness axiom, which is crucial for understanding limits and convergence, limits, continuity, and differentiability. These fundamental concepts are revisited with a more rigorous and analytical perspective, using epsilon-delta definitions and other formal tools. The behavior of sequences and series of real numbers is examined, including concepts like convergence, divergence, and uniform convergence, integration and Taylor series. Integration is studied more rigorously, and Taylor series are used to approximate functions. Heine-Borel theorem. This important theorem is used to study compactness in Euclidean space, which is crucial for understanding continuity and convergence in multiple variables. Distinction from basic calculus. Computational versus analytical. Basic calculus focuses on the computational techniques of differentiation and integration, while advanced calculus emphasizes the underlying analysis and proof techniques. Rigorous approach. Advanced calculus employs a rigorous mathematical approach, using formal definitions and proofs to establish the validity of calculus principles. Proof-based. A significant portion of the course involves writing and understanding mathematical proofs, which is a core skill for advanced mathematical study. In essence, advanced calculus provides a deeper, more rigorous exploration of the principles of calculus, equipping students with the tools and understanding necessary for more advanced mathematical studies. Linear algebra is a branch of mathematics that deals with vector spaces, linear mappings, and matrices. It's fundamental to many areas of mathematics, science, and engineering, providing tools for solving systems of linear equations, understanding geometric transformations, and modeling various natural phenomena. Here's a more detailed explanation. Core concepts. Vector spaces, sets of objects, vectors, that can be added together and scaled by numbers following specific rules. Linear mappings, transformations, functions between vector spaces that preserve these operations of addition and scaling. Matrices, rectangular arrays of numbers that can be used to represent linear transformations and solve systems of equations. Systems of linear equations, equations where each variable appears only to the first power. Key applications, geometry, understanding lines, planes and rotations in space. Engineering, modeling physical systems such as structural mechanics and control systems. Computer science, graphics, image processing and machine learning. Physics, relativity, quantum mechanics and electromagnetism. Mathematics, abstract algebra, functional analysis and differential equations. Economics and social sciences, modeling economic systems and social interactions. Why is it important? Modeling. Linear algebra provides powerful tools for modeling real-world phenomena by approximating complex systems with simpler linear models. Solving equations. It offers efficient methods for solving systems of linear equations which arise in many practical problems. Data analysis. Essential for various data analysis techniques, including dimensionality reduction, principal component analysis, and machine learning. Foundation for advanced topics. It serves as a foundation for more advanced mathematical concepts and their applications. Linear algebra, mathematical discipline that deals with vectors and matrices, and more generally with vector spaces and linear transformations. Unlike other parts of mathematics that are frequently invigorated by new ideas and unsolved problems, linear algebra is very well understood. The golden ratio, approximately 1.618, is a mathematical concept with deep connections to the Fibonacci sequence, geometry, and even the natural world. It's defined as the ratio of two quantities, where the ratio of the whole to the larger part is the same as the ratio of the larger part to the smaller part. This ratio is often associated with aesthetic appeal and balance, and while it's been claimed to appear in various natural and artistic creations, the scientific evidence for its prevalence is limited. Key aspects of the golden ratio. Mathematical foundation. The golden ratio is the limiting ratio of consecutive Fibonacci numbers, where each number is the sum of the two preceding ones, for example 0, 1, 1, 2, 3, 5, 8. Geometric representation. It can be geometrically constructed, using a line segment divided in a specific way. Fibonacci sequence. The Fibonacci sequence is closely linked to the golden ratio, as the ratio of consecutive terms approaches the golden ratio as the sequence progresses. Nature. The golden ratio is often cited in discussions about the arrangement of leaves on a stem, spirals in seashells, and the structure of sunflowers. However, the extent to which it truly governs these natural phenomena is a topic of ongoing debate. Human perception. There are claims that the golden ratio is aesthetically pleasing, but scientific studies on human perception have yielded mixed results. In summary, the golden ratio is a mathematical concept with a fascinating history and connection to the natural world. While it's often associated with beauty and balance, its prevalence and impact on human perception are subjects of ongoing scientific discussion. The golden ratio is found when a line is divided into two parts, such that the whole length of the line divided by the long part of the line is also equal to the long part of the line divided by the short part of the line. Pi is a mathematical constant, approximately equal to 3.14159, representing the ratio of a circle's circumference to its diameter. It's an irrational number, meaning it cannot be expressed as a simple fraction. Pi's value is crucial in various scientific fields and everyday applications, including geometry, trigonometry, statistics, and even physics. Here's a more detailed breakdown. Definition. Pi is the ratio of a circle's circumference, the distance around the circle to its diameter, the distance across the circle through its center. Irrationality. Pi's decimal representation is infinite and non-repeating, meaning it cannot be expressed as a fraction of two whole numbers. Importance in science, geometry, and trigonometry. Pi is fundamental in calculating the area, circumference, and volume of circles, spheres, and other geometric shapes. Physics. Pi appears in equations related to waves, such as light and sound, and in the Heisenberg uncertainty principle. Astronomy. Pi is used in spherical trigonometry to calculate distances between stars. Other fields. Pi also plays a role in probability, statistics, and even in understanding the patterns of stripes on zebras and spots on leopards. Historical significance. Pi has been known for over 4,000 years, and the Greek letter pi was first used to represent it in the 18th century by William Jones. Practical applications. Pi is used in various applications, including architecture, engineering, building and construction, and even software development, where it is used to test software. Probability is a branch of mathematics and statistics concerning events and numerical descriptions of how likely they are to occur. The probability of an event is a number between 0 and 1. The larger the probability, the more likely an event is to occur. This number is often expressed as a percentage, ranging from 0% to 100%. A simple example is the tossing of a fair, unbiased coin. Since the coin is fair, the two outcomes, heads and tails, are both equally probable. The probability of heads equals the probability of tails, and since no other outcomes are possible, the probability of either heads or tails is 1/2, which could also be written as 0.5 or 50%. These concepts have been given an axiomatic mathematical formalization in probability theory, which is used widely in areas of study such as statistics, mathematics, science, finance, gambling, artificial intelligence, machine learning, computer science, game theory, and philosophy to, for example, draw inferences about the expected frequency of events. Probability theory is also used to describe the underlying mechanics and regularities of complex systems. Trigonometry, from ancient Greek trigonon, trigonon, triangle, and metron, metron, measure, is a branch of mathematics concerned with relationships between angles and side lengths of triangles. In particular, the trigonometric functions relate the angles of a right triangle with ratios of its side lengths. The field emerged in the Hellenistic world during the 3rd century BC from applications of geometry to astronomical studies. The Greeks focused on the calculation of chords, while mathematicians in India created the earliest known tables of values for trigonometric ratios, also called trigonometric functions, such as sine. Throughout history, trigonometry has been applied in areas such as geodesy, surveying, celestial mechanics, and navigation. Trigonometry is known for its many identities. These trigonometric identities are commonly used for rewriting trigonometrical expressions with the aim to simplify an expression, to find a more useful form of an expression, or to solve an equation. Calculus is the mathematical study of continuous change, in the same way that geometry is the study of shape, and algebra is the study of generalizations of arithmetic operations. Originally called infinitesimal calculus, or the calculus of infinitesimals, it has two major branches, differential calculus and integral calculus. The former concerns instantaneous rates of change and the slopes of curves, while the latter concerns accumulation of quantities and areas under or between curves. These two branches are related to each other by the fundamental theorem of calculus. They make use of the fundamental notions of convergence of infinite sequences and infinite series to a well-defined limit. It is the mathematical backbone for dealing with problems where variables change with time or another reference variable. Infinitesimal calculus was formulated separately in the late 17th century by Isaac Newton and Gottfried Wilhelm Leibniz. Later work, including codifying the idea of limits, put these developments on a more solid conceptual footing. Today, calculus is widely used in science, engineering, biology, and even has applications in social science and other branches of math. Mathematical physics is the development of mathematical methods for application to problems in physics. The Journal of Mathematical Physics defines the field as the application of mathematics to problems in physics and the development of mathematical methods suitable for such applications and for the formulation of physical theories. An alternative definition would also include those mathematics that are inspired by physics, known as physical mathematics. Statistics, from German Statistik orig, description of a state, a country, is the discipline that concerns the collection, organization, analysis, interpretation, and presentation of data. In applying statistics to a scientific, industrial, or social problem, it is conventional to begin with a statistical population or a statistical model to be studied. Populations can be diverse groups of people or objects, such as all people living in a country or every atom composing a crystal. Statistics deals with every aspect of data, including the planning of data collection in terms of the design of surveys and experiments. When census data, comprising every member of the target population, cannot be collected, statisticians collect data by developing specific experiment designs and survey samples. Representative sampling assures that inferences and conclusions can reasonably extend from the sample to the population as a whole. An experimental study involves taking measurements of the system under study, manipulating the system, and then taking additional measurements using the same procedure to determine if the manipulation has modified the values of the measurements. In contrast, an observational study does not involve experimental manipulation. Two main statistical methods are used in data analysis: descriptive statistics, which summarize data from a sample using indexes such as the mean or standard deviation, and inferential statistics, which draw conclusions from data that are subject to random variation, for example, observational errors, sampling variation. Point 4. Descriptive statistics are most often concerned with two sets of properties of a distribution, sample or population. Central tendency, or location, seeks to characterize the distribution's central or typical value. while dispersion or variability characterizes the extent to which members of the distribution depart from its center and each other. Inferences made using mathematical statistics employ the framework of probability theory, which deals with the analysis of random phenomena. A standard statistical procedure involves the collection of data, leading to a test of the relationship between two statistical data sets, or a data set, and synthetic data drawn from an idealized model. A hypothesis is proposed for the statistical relationship between the two data sets, an alternative to an idealized null hypothesis of no relationship between two data sets. Rejecting or disproving the null hypothesis is done using statistical tests that quantify the sense in which the null can be proven false, given the data that are used in the test. Working from a null hypothesis, two basic forms of error are recognized. Type 1 errors, null hypothesis is rejected when it is in fact true, giving a false positive, and type 2 errors, null hypothesis fails to be rejected when it is in fact false, giving a false negative. Multiple problems have come to be associated with this framework, ranging from obtaining a sufficient sample size to specifying an adequate null hypothesis. Statistical measurement processes are also prone to error in regards to the data that they generate. Many of these errors are classified as random, noise, or systematic bias, but other types of errors, for example blunder, such as when an analyst reports incorrect units, can also occur. The presence of missing data or censoring may result in biased estimates, and specific techniques have been developed to address these problems. Logic is the study of correct reasoning. It includes both formal and informal logic. Formal logic is the study of deductively valid inferences or logical truths. It examines how conclusions follow from premises based on the structure of arguments alone, independent of their topic and content. Informal logic is associated with informal fallacies, critical thinking, and argumentation theory. Informal logic examines arguments expressed in natural language, whereas formal logic uses formal language. When used as a countable noun, the term a logic refers to a specific logical formal system that articulates a proof system. Logic plays a central role in many fields, such as philosophy, mathematics, computer science, and linguistics. Logic studies arguments which consist of a set of premises that leads to a conclusion. An example is the argument from the premises "it's Sunday" and "if it's Sunday then I don't have to work," leading to the conclusion "I don't have to work." One premises and conclusions express propositions or claims that can be true or false. Simple propositions also have parts like Sunday or work in the example. The truth of a proposition usually depends on the meanings of all of its parts. However, this is not the case for logically true propositions. They are true only because of their logical structure, independent of the specific meanings of the individual parts. Arguments can be either correct or incorrect. An argument is correct if its premises support its conclusion. Deductive arguments have the strongest form of support. If their premises are true, then their conclusion must also be true. This is not the case for ampliative arguments, which arrive at genuinely new information not found in the premises. Many arguments in everyday discourse and the sciences are ampliative arguments. They are divided into inductive and abductive arguments. Inductive arguments are statistical generalizations, such as inferring that all ravens are black based on many individual observations of black ravens. Abductive arguments are inferences to the best explanation, for example, when a doctor concludes that a patient has a certain disease, which explains the symptoms they suffer. Arguments that fall short of the standards of correct reasoning often embody fallacies. Systems of logic are theoretical frameworks for assessing the correctness of arguments.